Hi everybody, my name is UjwalGoli. I'm currently pursuing my final year at SRMAP University. Now I will be presenting you my project, which is titled Context Aware Information Retrieval Algorithm, in which I implemented the algorithm naming Context Aware Query Expansion using word embedding. This enhances the search system not only by giving the documents which contains the exact term, but also considers the user context and what the user really mean. Before moving forward, let us first discuss about the problems that we face while using the search engines. To demonstrate the problem, I am taking two users. One is a user A and another is a user B. They both differ by their context. One is a tech enthusiastic and another is a health conscious. But when they both type the same query, Apple, they get the result of Apple prices 2025. But user A wanted to get the information about the iPhone or MacBook prices, where the user B wanted to get the information about the market prices or the nutritious info about the Apple. Even though the query term was same, the context behind the query was different, which is based upon the user behavior and the context of the user. To fill the gap, the understanding what the user is really mean, the context-aware information retrieval comes into picture. Now you have understood that the problem that we face while using the search engines. This problem is primarily caused by the traditional information retrieval system. So to demonstrate the traditional information retrieval system, I will use the same example as before. Let's say the query was Apple. This system primarily focuses on the documents which contains the exact keyword that we used in the query and ranks the documents based upon how often this term is appearing in the document or how relevant it seems based upon the statistical models like TF and IDF and BM25. Even though this system was quicker and efficient, it fails due to it only focuses on keyword matching, not on focusing on the context of the user and what the user really meant. As of now, you know what is traditional information retrieval system and what are the drawbacks. Now let us discuss about what is context-aware information retrieval. Context-aware information retrieval is an advanced retrieval method that uses the user context such as topic, search history, or profile to personalize and improve search results. Instead of not only matching the keywords, it matches the meaning based on the user situations. So you can see here, the user plus the context is resulted to the expanded query, which results to ranking the results which are very relevant to the user. Now let us discuss about what is expanded query and what is the context-aware expansion of the query. So now let's understand what is a query expansion. Query expansion means adding related or similar terms to the original query so the system can find more relevant results. Context-aware query expansion means not only focusing on the query terms, but also focus upon the user context. It adds the terms which are more closer and similar to the user query as well as the user context, which helps the system to give more relevant results. Before moving forward, let us first discuss about the word embedding, which is the foundation of our algorithm. As you know that the machines doesn't really understand the raw data, they need to be converted into the numbers because the machines only operate on the numbers. They only understand the numbers. For the for that reason, the word embedding comes into play, which means representation of a word into a vector space or into the vector. Vectors allows us to measure the similarities between the words using percent similarities. So it demonstrates that the vectors or the words that have the similar meaning appear closely in a vector space. This helps the computer understand semantic relationships, not just text matching. Now let's discuss about the space of the vector. Word vectors exist in 100 to 300 dimensions, which is very large to see and to demonstrate in real world. So for that reason, we use a dimension reduction algorithm such as the PCA principal component analysis to reduce the dimension to the two-dimensional for visualization. This helps us to see the vectors of the query term, the candidate terms, as well as the context vector. As of now, you completely understand what is a context aware and what is a query expansion and what is a word embedding. Now let us combine these all, which is our final algorithm that I'm going to explain now. Initially, the algorithm takes 5 inputs, where the Q is a initial query terms, C is a initial context terms that we give it, and E is a pre-trained embedding model, which is essential for representing the words in a vector space, and alpha is a weighting factor between the query and the context similarity, which is essential for final formula that we will be discussing later, and K is the number of terms that we need to add to the original query. Now let us move on to the function, the main function. Initially, we have a set of context terms which are embedded in a vector space. Now we need a single context vector which represents the context of the user. For this reason, we will be averaging the every context term in the embedded model to create a single context vector. After that, we need a candidate set, which are the possible set of terms which can be added to the original query. So how do we create the list? For every query term in a vector space, you find the top n nearest terms for every query and group them into a candidate set L. Why? Because every term which is very nearest to the vector of the query represents their very close to the meaning or very related to each other. For that reason, we will be considering all the terms from all the queries. After that, after creating the candidate set L, for each term in the candidate set, you compute the similarity between the query terms, not only from the query that you have generated this, but also with respect to others. So the reason why we kept the formula like this was most of the times we have the query terms more than one. For that reason, only uh, finding this cosine similarity might increase the score. For that reason, we are averaging the score. After that, as we only have one single context vector, you can simply calculate the similarity using the cosine similarity. After that, input these two values in the final weighting score formula, which is seen, which is below here. Here, as you can see, the alphas here, which we initialized here, which represents how biased the score should be. If the alpha is larger, it means we are mainly concerned about the query terms, not upon the context. If our alpha is lower, it demonstrates that we are only concerned about the similarity with respect to the context, not on the query terms. This is more important, and the balancing between them is important also. After scoring all the candidate terms, sort them in a descending order, and pick the top K terms and add it to the query, original query. And yes, you have the query expansion, which also includes the context aware and also includes the word embedding. Before moving forward to the code execution, let us first discuss about the numerical example, which demonstrates the exact algorithm that we have learned. So initially, I give the query as a machine learning context for terms of the healthcare and the data. And as you can see, this is a 3D embedded for demonstration purpose only. Before moving forward to the code execution, let us first discuss the numerical example, which is directly demonstrates the algorithm that we have learned so far. Initially, I gave the query terms as a machine and learning, context terms as the healthcare and the data, and the candidate terms are here, Indian system training, education, and automation. You can see the 3D demonstrations of the vectors of each of the candidate terms and the terms. We converted it into the 2D space. You can see that for every query term, there are the uh, respective candidate terms. Here, initial step, we calculated the context vector, as we have multiple context terms. This is the average, and we calculate the normalized form of the context vector in order for the calculation of the cosine similarity. Pre-calculations. These are the similar pre-calculations for the rest of the terms. And here we calculate the cosine similarities between the candidate terms to the query terms and the context vector. Here we took the example of the training. These are the vectors representing the query as well as the context. Here is the dot product. And here is a cosine dot product by multiplication of normalized forms. As you can see, there are multiple number of query terms. You average it. Here is the average. Similarly, we do to the rest of the candidate terms. And we apply the formula for the every candidate term. We get the score. And then you sort based upon decreasing order and pick the k number of terms. Here is a k is 3. So basically you take the automation engine and training to keep it an expanded query. Before closing this presentation, I would like to execute the code which I prepared for explaining the algorithm. So here we load the data set which is already stored in our drive and store it as a data frame and load the GloVe and the embedded models. Here you can see that. After that, you take the queries and the context terms from the user. Here I already gave it as a school first and a student and teacher as the context terms. And then you find the candidate terms for each of the query terms. As you can see here, these are the respective candidates for query term school and for query term bus. After that, we will be visualizing the query term proximity candidates versus a distinct value. We can actually demonstrate which are non-relevant candidates and which are the relevant candidates to the query term. This is the query term and these are the respective candidate terms. Now, this is another example. And you calculate the similarity with respect to the query as well as the context. And this is the final score. You select the final kth one. And here the final, you took the k as a 3. So basically you are taking the terms as college, graduate, and school. And these are the just a visualization part. And you can see here, this is an optional thing where you represent the documents before and after the query expansion. Before the query expansion, the query terms for the school and bus. These are the documents that was ranked. And these are the query terms after the enhancement. And these are the documents that are resultant of this enhanced code, the enhanced query. So I would like to thank my professor for giving this wonderful opportunity to explore new algorithms and the concepts. I'm very grateful for him. Thank you.